Hello, my name is Anthony Tano, and in these set of slides I'll be presenting on reliability challenges in silicon carbide transistors. Here is a brief outline of the presentation. First, I'll be providing an introduction to power electronics. Following that will be an overview of silicon carbide technology, and the bulk of this presentation will be on the reliability challenges in silicon carbide transistors, specifically gate oxide reliability. And at the end of this presentation, I provide some industry advancements that have occurred over the past few years in regards to silicon carbide technologies. So with that, let's dive into an introduction to power electronics. So as we all know, silicon-based electronics consume a majority of the market, whether this is your conventional CMOS technologies, silicon on insulator or SOI, or bipolar. The majority of the market is fabricated on silicon wafers. However, the demand for specialized semiconductors is driving innovation. Some of these specialized semiconductors include gallium nitride, gallium arsenide, indium phosphide, aluminum gallium arsenide, and the topic of this presentation, silicon carbide. And the reason that we have this many specialized semiconductors is because these semiconductors contain different electrical and physical properties than conventional silicon, such as wider band gap, high electron mobility or high hole mobility, etc. So clearly the market for high power devices is growing. So this plot shows some of the major application areas of powered electronics plotted as a function of rated voltage. So if we start at the low spectrum or low voltage area of the graph, you can see some pretty simplistic electronic devices like DC to DC converters. If we go up in voltage at this medium voltage range, you can see the devices become a little more complex: motor control, electric vehicles. And at the high end of the spectrum, we have some very high power devices like power transmission and factory automation. What this plot is trying to convey to you is that as we increase in power, we're also increasing in the level of integration that needs to be taken place. Think about the electric vehicle, for example. Not long ago, electric vehicles were, there's very few electric vehicles on the market. And then now, as you know, with Tesla, these vehicles actually have become extremely integrated with regular electronics. For example, in your car, you have your GPS, and now even semi-autonomous driving capabilities. So essentially, this high-scale integration that is taking place with all of our devices, I'm pretty sure you've heard of IoT or Internet of Things. This high level of integration is what's really driving the need for power devices. Now let's dive a little deeper into silicon carbide technology specifically. So why silicon carbide? Well, there's few advantages and disadvantages of using silicon carbide, but some of the advantages I list here. For example, silicon carbide has a wider band gap than regular silicon. It has higher thermal conductivity, which means higher operating temperature, has a higher breakdown field, and lower on resistance. So let's look at the band gap for silicon carbide as an example. On the right, we plot the band gap energy in electron volts as a function of temperature for silicon and 3 different polytypes of silicon carbide. We'll touch on what polytypes are in just a little bit. So if we look at 300K, regular silicon has a band gap energy of about 1.1. But if we go all the way up to 4H silicon carbide, you can see that at the same temperature, it has about 3 times the band gap energy than regular silicon. This is evidence of why we would want to use silicon carbide for high power applications. Now, silicon carbide is a compound semiconductor that exhibits polytypism. What this means is that the material can adopt different crystalline structures which vary in one dimension, which we typically call the stacking sequence, without changes in chemical composition. So on the plot on the right, we have a ball and stick model of the different stacking sequences that silicon carbide can take. The naming conventions is first followed by a number, which refers to the number of layers in the stacking sequence, followed by a letter which describes the shape that the stacking sequence creates in a 3-dimensional space. So for example, in 3C silicon carbide, it means that it has 3 different layers that repeat periodically, and this creates a cubic structure. That's what the C stands for. It stands for cubic. In contrast, we have 4H silicon carbide, which means that there are 4 layers in the stacking sequence which repeat, and this creates a hexagonal structure. And lastly, we have 6H silicon carbide, which means that there are 6 layers in the stacking sequence, and this one also makes a hexagonal structure. So you can see that silicon carbide, while it has many benefits, such as the wide band gap and high thermal conductivity, it also gets a little more complex than regular silicon with these different stacking sequences, and we're going to look at some of the reliability challenges that this presents in just a couple slides. So here's a table that compares some of the other different types of semiconductor materials and the properties that they possess. So let's look at silicon carbide versus silicon to start. As we talked about earlier, silicon carbide has about 3 times the band gap energy of regular silicon. However, the electron mobility and hole mobility is much less. In addition, the thermal conductivity of silicon carbide is much higher than regular silicon, which means that this is well suited for high operating environments. And we can also make some comparisons to gallium arsenide and gallium nitride. I won't go through them all, but you can see that as we go through these different semiconductor materials, the band gap can be more or less the same, such as silicon carbide and gallium nitride, or they can vary widely, such as the mobilities between gallium arsenide compared to silicon carbide. So overall, there are some pros and cons that engineers need to consider when choosing the type of technology they want to design their circuit in. So to summarize, some of the advantages of silicon carbide are the high power and high operating temperature, the wider band gap, higher thermal conductivity, higher breakdown field, and low on resistance, as we discussed. But as we saw in the previous table, some of the disadvantages like lower channel mobility can hinder performance in some applications. Additional disadvantages that we'll discuss in the coming slides are high interface trap density. Silicon carbide also can have significant bias temperature instability, and as we saw in some of the stacking sequences, this can present a complex defect system compared to regular silicon and silicon dioxides inside of a MOS transistor. So now we're going to look at some of the reliability challenges in silicon carbide technology. So as we discussed previously, silicon carbide can crystallize in a wide variety of structures, and these can lead to different electrical, optical, thermal, and mechanical properties. So again, here is the same ball and stick model that we talked about previously with the different stacking sequences. You can see that in 3C, there's only 3 layers in the stacking sequence, and then that pattern repeats, and in 4H, there's only 4 layers and that pattern repeats, and so on and so forth. But what happens if the stacking sequence stacks incorrectly? So like silicon, a silicon carbide boule must be grown with a single desired polytype, whether it's 3C, 4H, or 6H. We want this crystalline boule to be as perfect as possible because we'll eventually cut it up into wafers and fabricate our microelectronics. However, mismatches in the stacking sequence can lead to stacking faults or dislocations. Down below are 2 photographs of the same stacking fault. On the left side is just a regular photograph through a microscope, and on the right is a photograph using atomic force microscopy. An atomic force microscope consists of a very tiny needle that scans across the surface of the silicon carbide wafer, and that needle will move up and down as it comes in contact with different heights in the topology. And what you end up with is essentially a map of the topology of the surface. And as you can see, these stacking faults have caused this cyclone or spiral shape on top of the wafer that ultimately end in a killer defect or a micropipe defect. A micropipe defect is essentially a giant hole in the silicon carbide wafer where the mismatches converge. So as you can see, this is one of the major defects that manufacturers are facing while trying to fabricate silicon carbide transistors. So dislocations in the semiconductor material not only occur in the bulk material, but it can also occur between materials. Misaligned stacking between silicon carbide and other semiconductor materials such as silicon dioxide can lead to interface traps. Interface traps are electrically active defects located at that interface between the oxide and the semiconductor. And these interface traps are capable of trapping and detrapping charge carriers, which has an adverse effect on device performance. On the bottom is a photograph of the transition between silicon carbide and silicon dioxide. And at this resolution, you can even see the silicon carbide stacking sequence. So interface traps would occur right in between the silicon carbide and silicon dioxide. And the adverse effects that these interface traps have can lead to bias temperature instability or even threshold voltage instability. Another plot on the right shows the atomic composition as a function of the distance from the surface, moving from silicon dioxide to silicon carbide. These interface traps would occur more likely at this transition region. Now let's take a closer look at gate oxide reliability for silicon carbide. Gate oxide reliability has been the most prevalent problem when it comes to fabricating silicon carbide microelectronics. And the reason being is that silicon carbide has a very high interface trap density. These interface traps are energetically very deep, which means that for whatever charge is trapped, it takes a very long time for that charge to detrap. This can lead to unstable threshold voltages and bias temperature instability. And what's much worse is that at very high interface trap densities, this can actually lead to premature oxide breakdown. Now remember the motivation for using silicon carbide semiconductor is to fabricate high power devices. If we have a very high interface trap density and our oxides break down prematurely, well, we're not going to have a very good transistor. As a frame of reference, here is the interface trap density for silicon versus silicon carbide. You can see the interface trap density for silicon is about 1e to the 9 or 1e to the 10 per square centimeter. And for silicon carbide, it's about 1e12 to 1e13 per square centimeter. So there's a very dramatic difference in interface trap density moving from silicon to silicon carbide. So how do we assess gate oxide reliability in general? Well, there's a couple different methods you can use. The first method, which is a very quick test, is a V-ramp test. During this test, you apply a voltage on the gate of a MOSFET or on a capacitor structure and monitor the leakage current through the gate oxide. Then as you ramp the voltage higher and higher, eventually you'll see a spike in the leakage current, and this is an indication that your oxide has broken down completely and has resulted in a short circuit. Alternatively, there is the constant voltage or constant current stress, which is typically used during time-dependent dielectric breakdown studies. Under this test, you apply a constant bias on the gate and again monitor the leakage current. As time passes, the leakage current will continually rise and eventually snap for certain technologies. Again, this is an indication that your oxide has broken down completely. So when we assess gate oxide reliability data, we typically take this failure data and plot it on a Weibull distribution. On the right, I have some fictitious data plotted on a Weibull plot. The data on the x-axis could be your breakdown voltage from your V-ramp test or your time to break down for your constant voltage stress. And on the y-axis is the Weibull probability. So for technology 1 in purple, you can see that there's a very wide variability. What this means is that the technology is not well controlled and the oxides break down at various different points along the x-axis. Technology 2, while slightly improved, still has an appreciable Weibull slope, but it is better than technology 1. And lastly, technology 3, which is in black, is the more ideal case for a stable process. The oxides appear to rupture roughly at the same voltage or time, which means that the process is well controlled. The ideal case would be a straight line up and down where all of our devices under test or DUTs fail at the exact same voltage or time. But again, this is only an ideal case and is not true to the real manufacturing process. So now let's discuss some recent industry advancements that have occurred over the past year. So just this last March, I actually attended the International Reliability Physics Symposium, or IRPS, for 2021. IRPS is one of the world's leading conferences for reliability physics hosted by IEEE. Here I list some of the attendees of that conference and their contributions that they either published or presented on. Wolfspeed, which is a silicon carbide manufacturer, actually started mass production of 4H silicon carbide transistors with 1200 volt application. These ones were specifically targeted for automotive applications. Infineon presented a method for determining the appropriate screening voltage for benchmarking gate oxide reliability. On Semiconductor characterized multiple defect types and their impact on device performance, stability, and projected lifetime. And lastly, STMicroelectronics correlated the breakdown of 4H silicon carbide MOSFETs to specific crystalline defects in the epitaxial layer using Fowler-Nordheim conduction screening techniques. So this brings us to the end of our presentation. In summary, silicon-based electronics still consume a majority of the market, but we are seeing an increase in demand for specialized semiconductors. The driver for this need has been the high level of integration for all of our IoT devices. These devices are now demanding that we have high power and also high efficiency. So silicon carbide has some advantages, such as its wide bandgap and high power and operating temperature, but its complex defect system makes it difficult to fabricate. In addition, the high interface trap density in silicon carbide has led to some reliability issues with the gate oxide that haven't been fully resolved. And as I just presented on the previous slide, recent industry advancements have made high voltage silicon carbide transistors commercially viable. So with that, thank you for watching, and I'm eager to see where we go in the future when it comes to these power electronic devices. Thank you. Here is a list of references.